So how does the gas stay in that shape?
I don't know. Okay, topic 1.6, work and energy. Here's the handout. I don't have a slide for you. We are going to define work as the product of displacement and the component of force parallel to the displacement when the force is constant. We will determine work from the area under a force position graph for any force. So more of that, find the area under graph. Describe work as a transfer of energy. We'll talk a little bit about that today. We will give examples of various forms of energy and describe qualitatively the means by which they can perform work. We will derive the equation for kinetic energy using W equals Fg cos theta in the kinematics equation. That's a lot of fun.
How much kinetic energy does the sun have?
It's moving. Kinetic energy is the energy of motion.
So that's a lot then.
It has more potential energy. We will derive the equation for gravitational potential energy near the surface of the Earth. We will do an experiment to determine Hooke's law with the spring. We will derive an equation for the potential energy of the spring using Hooke's law and a force displacement graph, and we will solve problems related to the conservation of energy. Wow, that sounds like a lot of fun.
Space unit.
Yeah. Let's talk first about energy. And you might want to highlight or underline or something other as we go here. Energy is the most central concept that underlies all of science. Really. Energy is sort of fundamental. But if I ask you, Zach, what is energy? What would you say?
The most central concept.
No. Come on. Give me a definition. Energy is... Yeah, but define energy. What is energy? You can't really sort of... Yeah, it's just not easy to define. Surprisingly, the idea of energy was unknown to Isaac Newton. Hard to believe that. And its existence was still being debated in the 1850s. The concept of energy is relatively new, and today we find it ingrained not only in all branches of science, but also in nearly every aspect of human society. We're all quite familiar with it. Energy comes to us from the sun in the form of sunlight. It is in the food we eat, and it sustains life. Energy may be the most familiar concept in science, yet it is one of the most difficult to define. Everybody knows what it is, but you can't define it. Persons, places, and things have energy, some more than others. But we observe energy only when something is happening. Only when energy is being transformed. We will begin our study of energy by observing a related concept, work. And I'd like to just highlight that thing right there. We observe energy. Oops, I wanted to highlight it. We observe energy only when something is happening, when energy is being transformed. Do you see all the energy I have in my body? As I just sort of stand here? But if I start running around like a lunatic, I'd be burning up energy, wouldn't I? Right?
Do it. Let's test this theory.
Or if I was dancing, like I'm now dancing, Stefan. All right, work. The last chapter showed how changes in an object's motion are both related to force and to how long the force acts. That was actually 2 chapters ago on momentum. How long meant time, but the quantity of force times time is called impulse. But how long need not always mean time. It can mean distance as well. When we consider the quantity force times distance, we are talking about a wholly different quantity, a quantity called work. We do work when we lift the load against the Earth's gravity. The heavier the load or the higher we lift the load, the more work is done. 2 things enter into every case where work is done. The exertion of a force and the movement of something by that force. So those 2 things are required before you have work. There has to be an actual force, and there has to be movement. So, if I stand here and I push against the filing cabinet, but it doesn't move, I'm applying a force. Am I doing work? Am I doing work when I push on the filing cabinet but it doesn't move? Is there movement? Must be movement for there to be work. Let's look at the simplest case in which the force is constant and the motion takes place in a straight line in the direction of the force. Then the work done on an object by an applied force is defined as the product of the force and the distance through which the object is moved. In shorter form, W equals Fd. There's your formula. It doesn't need to be derived. It's a definition. Work is defined as force times distance. If you lift 2 loads 1 story up, you do twice as much work as you do in lifting 1 load because the force needed to lift twice the weight is twice as great. Similarly, if you lift the load 2 stories instead of 1 story, you do twice as much work because the distance is twice as much. Now, the definition of work involves both a force and a distance. A weightlifter who holds a barbell that weighs 1,000 newtons overhead does no work. He's just standing there holding it. No work. Whoops. No work. He may get really tired doing so, but if the barbell is not moved by the force he exerts, he does no work. Work may be done on the muscles by stretching and contracting, which is force times distance on a biological scale, but this work is not done on the barbell. Lifting the barbell, however, different story. When the weightlifter raises the barbell from the floor, he is doing work. Work generally falls into two categories. One of these is work done to change the speed of something, and the other kind of work is bringing an automobile, this kind of work is done in bringing an automobile up to speed or in slowing it down. So a change in speed is work. The other category of work is the work done against another force. Like when an archer stretches her bowstring, she's doing work against the elastic forces of the bow. When the ram of a pile driver is raised, it is exerted against the force of gravity. When you do push-ups, you do work against your own weight. You do work on something when you force it to move against the influence of an opposing force, even against friction, right? Work. The unit of measurement for work combines the unit of force, the Newton, with the unit of distance, the meter, and the unit of work is surprisingly, the Newton meter, which has been defined to be the joule, which rhymes with pool. 1 joule, symbol capital J, of work is done when a force of 1 Newton is exerted over a distance of 1 meter, as in lifting an apple over your head. For larger values, we speak of kilojoules or megajoules. A weightlifter does work on the order of kilojoules. The energy released by 1 kilogram of fuel is on the order of megajoules. Okay, so if you went and you got like a can of gas, you're talking about megajoules of energy. Okay, now who's got a snack with them today? Anybody got a snack with them? No? I need like a nutritional content or something. No one's got snacks? There's always someone that's got something.
I drew a kitty cat.
All right, I'll dig into the recycling. All right, so on the back of this Minute Maid orange juice bottle, it says calories 220. What does that mean?
Calories, amount of energy required to burn to boil 1
gram of water.
Gram of water.
Raise it 1 degree, right?
Yeah.
In
centigrade.
Centigrade. Okay, so in other words, what does that mean about the 220 calories in the orange juice then?
That'll raise lots of centigrades.
So drinking the orange juice is going to make me warmer?
Yeah.
Really?
Well, your body has to work. That's how much energy has to be.
Yeah. Now, well, I thought it said joules. Joules was the unit of energy.
Yeah, well, what's the unit of calories?
Calories and joules measure the same thing. And actually, the big C calories are different from small c calories. The calories that you learn about in science, the 1 centigrade 1 thing, that's actually a small c calorie. The big C calories are actually kilocalories. But that sounds too nerdy to put on orange juice bottles, so they just put a big C on. Okay? The only food that I've ever seen that lists the nutritional content, the energy in joules, I want to take a guess. I've only ever seen it on 1 food.
Cereal.
1 kind of cereal. Vector cereal. It's the only one that I've ever seen it has it in. It's actually megajoules. How did you know that, Jordan? And you've wondered what that was. Well, now you're going to know. Okay? Yeah, it's actually megajoules, I think, isn't it? Yeah. Okay. And you're gonna try and figure out when you're running the stairs. You're gonna try and figure out how long you have to run those stairs to burn off that bowl of vector.
A long time.
Surprisingly long.
It's like half an hour.
Surprisingly long.
Like
Well, it depends how fast you do it. Okay, let's talk about power now. The definition of work says nothing about how long it takes to do the work. When carrying a load up some stairs, you do the same amount of work whether you run or walk. So why are you more tired after running upstairs in a few seconds than after walking upstairs in a few minutes? To understand this difference, we need to talk about how fast the work is done, or the power. Power is the rate at which work is done. Power is the rate at which work is done. It equals the work done divided by the amount of time in which the work is done. So again, it's a definition. You can't derive this formula. It's defined. Power equals work over time. Power equals work over time. An engine of great power can do work rapidly. An automobile engine with twice the power either does not necessarily produce twice as much work or go twice as fast as the less powerful engine. Twice the power means it will do the same amount of work in half the time. The main advantage of a powerful automobile engine is its acceleration. It can get the automobile up to a given speed in less time than less powerful engines. So your cars like your Mustangs and whatnot can have a lot of horsepower. What does that mean?
They can work hard.
Exactly. They can do work quickly.
This is when we're going to go running up.
We're going to running up the stairs. You're going to determine your own horsepower. How powerful are you?
Oh, I think Packers in that season.
Yeah. Well, it depends on how fast you are. It all depends on how big you are, too, right? Bigger people, to do well in the lab, bigger people have to be fast as well. Like Dooley was fast, right? Not as big as Quinn, right? So he's actually got to go. He's actually got to go faster.
I wonder what you can get the most efficiency. 1 stair, 2 stairs, 3 stairs.
I don't know.
I'd say probably 2 stairs. That's like a solid, easy pace.
Yeah. Yeah. Okay. So we can look at power this way. A liter of gasoline can do a specified amount of work, but the power produced when we burn it can be any amount, depending on how fast you burn it. The liter can produce 50 units of power for half an hour in a car, or 90,000 units of power for 1 second in a supersonic jet aircraft. Okay. The unit of power is the joule per second, also known as the watt. Named in honor of James Watt, who was not the inventor of the steam machine, but was the developer of the steam engine. 1 watt of power, W, is expended when 1 joule of work is done in 1 second. Kilowatt is 1,000 watts. A megawatt is 1,000,000 watts. In the U.S. and Canada, we customarily rate engines in units of horsepower, electricity in kilowatts, but either can be used. In the metric system of units, automobiles are rated in kilowatts. And if you look inside the little decal on your car, they will usually talk about the horsepower of the engine, but they'll also list the power in kilowatts as well, sometimes. 1 horsepower is the same as 0.75 kilowatts. So an engine rated at 135 horsepower is about a 100 kilowatt engine. Okay? Your lawnmower, what would a lawnmower run at horsepower-wise? Anybody know? Oh, that's pretty high. Like 3-4 horsepower is what a lawnmower engine would run at.
But then when you put it in a go-kart, it goes really fast.
Well, yeah, I mean, you probably don't need that much horsepower on a lawnmower. Snowblower, you need more horsepower. How come? You got to throw stuff, right? I mean, the lawnmower is
one
just,
of those massive lawnmowers.
yeah. I mean, all it's doing is cutting grass, right? It doesn't require a lot of power.
Yeah, but when you're driving,
If it's thick grass, then yeah. The 3 main engines of a space shuttle can develop 33,000 megawatts of power when fuel is burned at the enormous rate of 3,400 kilograms per second. 3,400 kilograms per second.
What?
This is like emptying an average-sized swimming pool in about 20 seconds. So imagine the pool here, emptying it in 20 seconds. That's how fast the fuel is burned in the space shuttle.
Where the heck did they I mean, I know the tanks are big, but
Yeah, but it's crazy.
I guess you wouldn't need that much as soon as you're out of the first.
Once you get moving,
100 feet.
object in motion stays in motion, right? Yeah.
It's ridiculous.
It is.
No wonder NASA
Well, the thing is, the more fuel you put in there, the heavier it gets, which means the more fuel you got to put on there, right? So it's sort of they really try and make everything as light as possible to minimize the amount of fuel needed.
What's their calculations are on? That's
Well, I'm sure they put a little bit of reserve. Yeah. Now, mechanical energy, work is done by an archer drawing the bow. The bed bow has the ability of being able to do work on the arrow. When work is done to raise the heavy ram of the pile driver, the ram acquires the property of being able to do work on an object beneath it when it falls. When work is done to wind a spring mechanism, the spring acquires the ability to do work on various gears to run a clock, ring a bell, or sound an alarm. In each case, something has been acquired. This something, which is given to the object, enables the object to do work. This something may be a compression of atoms in the material of an object. It may be a physical separation of attracting bodies. It may be a rearrangement of electric charges in the molecules of a substance. This something that enables an object to do work is called energy. There's your definition. Energy is something that enables an object to do work.
what we said. Or has the potential.
exactly. So when I have my bottle of orange juice and I ingest my 220 calories, that just means I've taken in enough energy
Do work.
to do some work.
You always need energy, otherwise you can't do work.
What happens if I don't do work with my 220 calories?
Your body starts to burn.
It starts to store it in the form of fat, right? Yeah. Okay, so, I mean, basically, it's the energy that we eat or drink on a daily basis is used to sort of power your body on a regular basis, kind of. If you burn more than you ingest, guess what? You start burning some fat. If you ingest more than you burn, well, you make some fat.
Storing some fat.
Storing some fat. Like work, energy is measured in joules. It appears in many forms, which will be discussed in the following chapters. For now, we're going to focus on mechanical energy, the energy due to the position or movement of something. Mechanical energy may be in the form of either potential or kinetic, and we're going to look at both of them. Is that as far as I've gone? Oh, we've got a little bit more. So let's talk about potential energy. We're almost done. An object can store energy by virtue of its position. The energy that is stored and held in readiness is called potential energy. You all have potential energy stored as fat in your bodies. Because in the stored state, it has the potential for doing work. A stretched or compressed spring, for example, has the potential for doing work. When a bow is drawn, energy is stored in the bow. Stretched rubber band is potential energy because of its position. For it's part of a slingshot, it's capable of doing work. The chemical energy in fuels is potential energy, for it is actually energy of position when looked at from a microscopic point of view. It's talking about like the electrons going higher shells and stuff. This energy is available when the positions of electric charges within and between the molecules are altered. That is when a chemical change takes place. Any substance that can do work through chemical action possesses potential energy. Potential energy is found in fossil fuels, electric batteries, and the food that we eat. Work is required to elevate objects against Earth's gravity. The potential energy due to elevated positions is called gravitational potential energy. Gravitational potential energy. Water in an elevated reservoir and the roundabout pile driver has gravitational potential energy. The amount of gravitational potential energy possessed by an elevated object is equal to the work done against gravity lifting it. The work done equals the force required to move it upward times the vertical distance moved. The upward force required is equal to the weight mg of the object. So the work done in lifting it through a height h is given by the product mgh. Potential energy, mgh. I'm giving you all the formulas right up front. We'll revisit them in a bit. Note that the height h is the distance above some reference level, such as the ground or the floor of a building. The potential energy, mgh, is relative to that level. It depends only on mg and the height h. You can see in the figure below that the potential energy of the boulder at the top of the ledge does not depend upon the path taken to get there. And they have a picture here. Okay, so there's a little picture there. You have the questions at the bottom. Okay, I'll give you a couple minutes while I do my attendance. You guys can talk amongst yourselves and see if you can come up with a couple answers there. Question 1, how much work is done on a 100 Newton boulder as you carry it horizontally across a 10-meter room? Why is it 0?
For what?
The first one. Why is the first one 0? Well, as I walk across the room, there's a stick figure of me carrying a red rock across the room. Okay, so like over here, I've walked across the room. Have I added any energy to the rock? Does it have any more energy than it did before? No, I've not transferred any energy, therefore, no work is done. Mr. Bennett, you told me that as long as there's a force and there's motion, there's work. However, well, I sort of glossed over a little bit. The force and the motion have to be in the same direction. Force now. Granted, do you need a little bit of force to get it going?
They can push it off.
Well, I mean, if I'm just carrying it, really, I'm just accelerating, right? There is a small amount of work done right at the start, but once I get it up to speed, I'm not adding any potential energy. Virtually 0, exactly. How much work is done on a 100 Newton boulder when you lift it a meter? Instead of carrying it across the room, I actually lift it. Well, that's m times g times h. The m and the g is already done for you. It's 100 times 1 meter. The answer should be 100 joules, right? 100 joules.
Over T?
No, that's power.
And
We're talking about work here. Now, what power is expended if you lift it this distance in 1 second? Now you take your work, your 100 joules, divided by a second, 1 second. Now you're talking 100 watts. Okay, many of us, don't we have like 100-watt light bulbs in our homes?
Yeah,
What does that mean, 100-watt light bulb? It means that every second you're getting 100 joules of energy, some of it in light, some of it in heat. How come a 100-watt light bulb is brighter than a 60-watt light bulb? Gives off more joules per second. It's brighter. Now, those old style light bulbs there, the incandescent ones, most of that 60 watts is actually given off as heat, which is why the new curly ones, I think it's like 13 watts of energy. How come you can get just as much light out of it? Because there's not as much heat. So like 47 watts of energy is the actual heat given off. They're not very efficient. What is the gravitational potential energy in the lifted position? Also, the energy is measured in joules, 100 joules. Now, if you look here at this picture, does it matter how the boulder got to that cliff? Does it matter how it got there, or does it still have the same amount of gravitational energy? Whether you lift it, roll it up the ramp, or carry it upstairs. It has the same potential energy. Okay, it doesn't matter. Now, which one would require less work? Which one would require less work? Yeah.
No, not
Yes. Mary, which one would require less work? Putting the boulder up on the ledge, rolling it up the ramp, or carrying it up the stairs?
rolling.
Well, most people would say it would be easier to roll it, but that doesn't necessarily mean that it's
They
less
can't figure out
work.
which one's wrong.
In fact, they're all the same.
No.
It has 200 joules of energy at the end, which means you needed to come up with 200 joules of work. How come you say, Mr. Bennett, it would be easier if I rolled it up the ramp? The difference is you would need a certain amount of force here. Going up the ramp, you would need a smaller amount of force. But a longer distance, exactly. So F times a bigger D, here I have a small d, gives me equal size works. Now, having said that, when you roll it up the ramp, there's actually some friction, so you'd actually need a little bit more force, so there's technically a little bit more work done when you roll it up the ramp. But people prefer to do a little bit of force, less force, over a longer distance than more, because it's easier. Yeah, you can't. Most people can't come up with that kind of force.
For C, it's like medium force.
Sort of, because you're sort of just doing it in steps, right? Yeah, exactly. All righty.